So you're given a function here that is a velocity function. So you have Yvonne is running and her velocity is given by v of t. And so then the first question is, what quantity does the area of the rectangle in the graph approximate? And so one thing you can think about is, so the velocity v of t is measured in meters per minute. And t is measured in minutes. And when you think about this rectangle, the area of this rectangle is a t times a v of t. So when you multiply v of t times t, if you think about the units, it's going to be meters per minute times minutes. And that will give you something, an answer that's in meters. So that rectangle represents some amount of meters. So that will kind of help us to narrow down what we have. So it's not an average velocity. This one is a distance away from home, so that's an amount of meters. So that's a possibility. It's not about velocity. It's not about acceleration. So it's either B or E now. So is it Yvonne's distance away from home 3 minutes after she started running? Or is it the change in her distance away from home over the interval of time from 3 to 4? So since this is only over the interval of time from 3 to 4, it's an approximation of this thing, her distance, the change in distance from 3 to 4. And this is going back to the section in the textbook that tells us that the integral of a rate is the change in position. S of t2 minus S of t1. So the net change is the integral of the rate. So this was a section in the textbook. Okay, and then it says, what quantity does this sum approximate? So if I look at this sum, I am computing the velocity at 1, the velocity at 1, the velocity at 3 halves, the velocity at 2, at 5 halves, at 3, and at 7 halves. So if I put that on here, so that's at 1. So all of these time periods, we're computing the velocity, and we're multiplying it by this 1/2, which is, so what we're really doing is we're computing this. Sorry, we're supposed to be doing a left-hand sum here, yeah. So the left-hand sum would be there. Okay, so that's what we're computing with these rectangles. So you can think of it as the height of the rectangle times the width. And so if we look at that, that's going to be approximating the area underneath that curve, or the integral of the velocity function from 1 to 4, and this is a left-hand sum. So the integral of that velocity function, the integral of that rate function, will be the change in position. So this is representing a change in position. So if we look at this, so it's not a change of her velocity. Is it the change in her distance away from home? Possibly. It's not her acceleration. And it's not her instantaneous velocity. Is it the distance away from home after running 3.5 minutes? No, because all we know is the change from 1 minute to 4 minutes. So the answer is B. So this tells us a ball is being thrown. The height of the ball above the ground is modeled by that function. And so we can see that that is a parabola that's upside down like this. Here's t, and here's g of t function. And so at this point, by solving which of the following equations can we determine the value of t for which the height of the ball is maximized? So that would be at this height, this value of t, we're looking for where the derivative is 0. So what I can do is I can take the derivative of that function. So what's the derivative of that function? G prime of t is negative 32 plus 31.829. And if I take that derivative function and set it equal to, well, at the maximum, the slope would be 0. Whoops. At the maximum, the slope would be 0. And so I want to set that derivative function equal to 0. T plus, that's this one. If we set it equal to 0 and solve for t, that'll tell us the time when that maximum is reached. Here we're given a graph of f prime. So based on the graph of f prime, for what values of x does f of x have a maximum value? So we're going to use the first derivative test. And so if I think about f prime, for what values of x is f prime equal to 0? F prime is equal to 0 here, 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 and here. So at -8, whoops, -8, -4, 1, and 4 are where f prime is equal to 0. And let's look what's happening to the left and right of each of these. So when we are to the left of -8, my function is below the x-axis down here, so it's negative. Between -8 and -4, my function is still below the x-axis, so we have negative x values, or negative values of my derivative. Between -4 and 1, I have positive y values. Between 1 and 4, I have negative y values. And after 4, I have positive. And so what does that mean about the function f? These are values of the derivative, right? So that means f is decreasing, then f is increasing, then f is decreasing, and then f is increasing. So if f prime is negative, f is decreasing, and if f prime is positive, f is increasing. And so where do we see that there would be a maximum? Well, I want to go from increasing to decreasing. So that happens here at x equal 1. So that's the answer. Okay, then it says a portion of the graph of f passes through the point C, f of c, which of the following conditions are satisfied? So let's think about what we're given here. The first little bit here, if I look at this first part, is talking about the derivative. And if I look at this portion of the graph, since the function is always decreasing, I know that f prime of c is always less than 0. So I can rule out a and b. Then I know if I look at this that f is concave up when x is less than c. So f double prime of c is positive when x is less than c. So let's look for that one. So this one can be ruled out. F prime of c is less than 0 because this part fails. F double prime is should be greater than 0 for x less than c. Okay, let's see if this one works. And we know here f double prime of c is less than 0 because it's concave down when x is greater than c. So let's see if that part holds. Yep. So C is the correct answer there. On number 2, it says to use calculus to determine the following for the function. Find the critical points. So to find critical points, I need to take the derivative. And the critical points occur when the derivative is either 0 or when the derivative is undefined. Now, if I look at this function, it's just a polynomial. So the derivative will always be defined everywhere. So the only way we can get critical points is if the derivative is 0 for this kind of function. So let's find f prime. So it's 6x plus 6x squared plus 6x minus 12. And if I set that equal to 0, I can pull a 6 out of everything, and I can factor. So my critical points are x equal -2 and x equal 1. So those are my critical points.